A very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be talking about local equilibrium equations. So let us get started. The topics for today's lecture are on force equilibrium and moment equilibrium. So we'll be considering bodies which are in equilibrium, and then we'll be applying the equations of force equilibrium and moment equilibrium to derive some interesting results. So let's get started. So we'll be performing force and moment equilibrium or force and moment balance for bodies which are under equilibrium. So let us talk about what is the meaning of equilibrium. So we talk in terms of force equilibrium when the net force acting on a body is zero, that is, there is no acceleration of the body. And we also write that the net moment or the net moment of the forces acting on the body is also zero, but since moment has to be defined around a point, so we say that the net moment of all the forces acting on the body around any point is zero, which basically means that there is no angular acceleration or there is no rotating omega, because you can also get where a moment can also result in the axis of rotation rotating like you have in gyroscopes. So this is the meaning of equilibrium. But this is not just true for the whole body, because if you take a small subset of the body, even that part is under equilibrium. So the same conditions can then be applied to that subset or the sub-volume in the body. So for any part of the body, these equations hold if the whole body is under equilibrium. So the aim of today's lecture is to use these ideas on some arbitrary part of the body to get equations which involve tractions. And these equations will be valid at each and every point in the body, which is why they'll be called local equilibrium equations. So let us start with the force equilibrium first. So let's say this is a part of the body, or I would rather say an imaginary part, because I'm not cutting the body in this shape. The body as a whole could be larger, and you're imagining some subset of the body. Now this body has a bounding surface area like this. So this we'll call gamma. The volume of the body as a whole we'll call omega, the same convention that we have been using in this course. And if I take an infinitesimal volume in the body, so if I try to break this omega into small infinitesimal volumes, I call this as a d omega. And if I talk about infinitesimal surface areas on the surface of the body, then I could call this as a d gamma. And since surfaces have to be denoted using a unit normal, so I call this as a unit normal n hat. So with this understanding, let's write the force equilibrium equation on this part of the body. So we'll write the net force acting on the body as the sum of surface forces and volume forces or body forces. So when I write surface forces, they are basically sum of all the forces acting on the enclosing surface of the body. So if I start taking these small d gammas, I find the traction vectors on these d gammas. So this traction vector for this particular d gamma is t n hat. And what I do is I write this traction vector on the n hat plane times d gamma. So that gives me the small amount of surface force acting on this small surface. And then I integrate this over the complete surface gamma. And since it's a closed surface, so this becomes a closed integral. So this integral represents the sum of all the surface forces acting on the surface of this imaginary subset of the body. And now we'll add the volume forces or the body forces. If this is the small volume d omega that we're talking about, there will be some force, some body force acting on this volume, which will be rho times the vector b times d omega. So this is the body force acting on this small infinitesimal volume d omega, and I'll add all such forces over the complete volume omega. So for each sub-volume in different parts of the overall volume, I'll calculate the force and I'll add them together, which basically is this integral. So there's a sum of these two quantities, and this is equal to 0. So this equation is our starting point of the force equilibrium equation. And this is coming from the fact that the net force acting on this body, or whatever this imaginary part is 0. If this is the case, then the body is under force equilibrium, that is, the body does not accelerate in this case. Now what we do now is we apply the Cauchy stress formula. So this allows me to write the traction vector at the n hat as sigma ji times nj times d gamma. And then you have the volume integral, which stays as it is. So now I've written this in the indicial notation. Right, and the next step now is to convert this surface integral into a volume integral, which can be done using the Gauss's theorem. So apply Gauss's theorem, and we are doing that on the area integral to convert that to a volume integral. So now this becomes a volume integral, and you have a sigma ji nj, so this becomes a sigma ji comma j times d omega. If you want, you can go back to the Gauss's theorem. In fact, let me write that down. So this theorem said that the surface integral of a quantity Cijk dot times nq d gamma is equal to the volume integral of the quantity Cijk dot comma q times d omega. So in this case, the quantity C is simply sigma ji and nq is an nj. I'll complete the equation. And please recall that to apply the Gauss's theorem, we've assumed that the quantity sigma ji is smooth, because you want to take a derivative of that. So if it is not smooth, if it is discontinuous, this derivative cannot be taken. So this is not valid. So let's combine the two terms now. This becomes an integral over omega of sigma ji comma j plus rho bi times d omega is equal to 0. So this is basically a sum of this quantity multiplied by a d omega, and it is summed over all the infinitesimal volumes. So you basically move the infinitesimal volume, calculate this quantity at the center of the infinitesimal volume, and multiply by d omega and add them all together, so that you are able to find this quantity over the complete omega. But the choice of omega in this case is arbitrary. In fact, what I could do was I could take my d omega in this body like this as the complete body. So what that would mean is that this quantity or the integrand in this case has to be identically equal to 0 because the choice of omega is arbitrary. So the integrand has to vanish, that is, this quantity is 0. And where is it 0? Well, it is 0 everywhere because we're talking about this sum being applied for different arbitrary bodies. So if I take d omega as the only complete body, then this is 0, and anywhere I take this d omega, this quantity is a 0. So this means that this quantity is a 0 everywhere inside the body. So this integrand has to vanish everywhere in the whole body. So whole body is basically the complete domain where the quantity sigma would be defined. Anywhere outside it, it will have no meaning because we're talking about an object which has certain boundaries. So this allows us to write sigma ji comma j plus rho times bi equal to 0, and this equation is famously called local equilibrium equations. And why do we call them equations? That's because this represents a set of three equations. There's one for, well, I can write it as sigma j1 comma j plus rho b1 equal to 0, which actually can be expanded to plus rho b1 equal to 0, and I'll write the other two as well. So this local equilibrium equation, it represents these three force balance equations. So these equations have to be satisfied for an object to be in equilibrium, and these equations have to be satisfied at each and every point inside the body. Even if at one point inside the body these equations are not satisfied, that would mean that that point would not be under equilibrium, and therefore the body as a whole could not be called as under equilibrium. So now that we have written the local equilibrium equations for force, let's move on to moment equilibrium. So again, we have a body, or I could say a part of a body, and since we are taking equilibrium, so I would write moment, which is a vector actually, and for equilibrium, moment equilibrium, the moment about every point in space has to be 0. So if the moment equilibrium equation holds around every point in the space, I can apply moment equilibrium about any point. So let's take the origin for convenience. So let's say this is the origin here, and I take the moment about the origin and I'll write this equal to 0. That's because the moment about any point is 0, and this is the moment about origin. So how do we calculate the moment acting on the body? Well, for that we have to talk about forces, because moment of a force is the vector x, that is the vector joining from the origin to that point where the force is acting, cross the force. So forces are of two types. One is surface forces and the other are body forces. So we'll start with the moment of surface forces. So let us say that we have a point on the surface which has a normal n hat. We'll call this surface area as d gamma, and the traction acting on this is Tn hat. So the moment about the origin because of this Tn hat will be given as the cross product of the vector x cross this force Tn hat times d gamma. So let's write it down. So the vector x cross the force which is Tn hat times d gamma, and this is just the moment of this force acting on this small area. But as I integrate this over the complete enclosing surface gamma, this will give me the moment of all the forces acting at different points on the surface. To this I will add the body force integral. So let's say you have a small volume which is d omega, and there's a body force rho times b, that is the force. So if I want to find the moment of this, I'll simply take this as x, which is the general position coordinate, cross rho b d omega, and this is integrated over the complete volume omega. Now as I do the integral, the position vector will change because I am changing the volume of the surface elements in the integrals. So the x vector that depends on the position of the infinitesimal volume or infinitesimal area, and that is the reason I have written the position vector as x vector. So this x vector is simply xi ei. So as a summary, this is the integral of all the moments of the surface forces acting on the body, and this is the sum of all the moments of the body forces acting on the body. In addition to this, we can have concentrated moments at the point, in this case the origin as well, and these concentrated moments are sometimes also called couples. So we could have a body couple or a surface couple, but it is only for a very special class of materials that we have these concentrated moments existing, and these class of materials are called polar materials. But since these materials are very rare in general usage, so we'll assume that we are dealing with non-polar materials, which 99.99% of the cases in general are. So what that means is that these are the only two moments possible, and this is equal to 0, the sum of these, because the net moment on the body around the origin is 0. So let's write this balance in the initial notation now. So we have a cross product of two vectors. So this can be written as epsilon ijk xi, that's the first vector, tj, that is the second vector, times d gamma. I'm not writing an ek hat because we tend to use the misuse notation. So we'll not be writing ek hat of the vector basis vectors here, plus an integral. Now we have an integral over omega, and then again we have a cross product. So this becomes epsilon I jk xi, and then we have a rho bj d omega, and this is equal to 0. So now we'll call this as 1 and this as 2. So let's simplify 1 first. So if I apply the Cauchy stress formula in this case, this becomes epsilon ijk xi, and this Tjn hat now becomes a sigma Pj Np times d gamma. I'll write it down using the Cauchy stress formula, which states that Tj in this case is sigma Pj Np. So we can now apply the Gauss's theorem. So we have a quantity times Np integrated over d gamma. So this quantity is our Cijk dot dot dot. So we apply the Gauss's theorem. So this becomes an integral over omega now. Epsilon ijk xi sigma pj comma p times d omega. So let's expand this. So epsilon ijk is simply a constant, so it does not participate in the derivative. And then we have an xi times sigma pj comma p plus an xi comma p times sigma pj times d omega. Let's see if we can expand this further. This stays as it is, but this xi comma p is nothing but delta ep times sigma pj, and I can apply the substitution property of delta now. So this becomes a sigma ij d omega. So this is the first term, and the second term is a volume integral, so we'll not touch it right now. So now let's combine, so let's call this equation A. So we'll write substitute back in A. So this becomes integral over omega epsilon ijk times xi times sigma pj comma p plus epsilon ijk sigma ij plus, and now we have part 2 in equation A, which is also a volume integral. So I can add sigma ijk xi rho bj to that term as well. So this is an epsilon ijk xi rho bj, and this whole is multiplied by a d omega, and this is equal to 0. Now using the same idea as earlier, that we are integrating this quantity, this large quantity, over an arbitrary sub-volume. So what that means is that this quantity has to be identically 0, because my choice of sub-volume for integrating or creating the sum is arbitrary. I could even choose just one infinitesimal volume as the complete volume, and that would basically mean that this quantity is 0 at each and every point inside the body. So I'll combine the first and the third term together. So epsilon ijk xi becomes common, and then we have a sigma pj comma p plus rho bj, and then we have the third term, which is epsilon ijk times sigma ij, and this is equal to 0. Now let's look at this term in parentheses, and this we had shown to be 0. So this is equal to 0. From the local equilibrium equation. So that means this term vanishes. So all we are left with is epsilon ijk sigma ij is equal to 0. Let me box this. So this is the equation that we get by applying the moment equilibrium on the body or any subset of the body. But this can further be expanded because I and j are repeated indices. So let's do that. In fact, let's do it for 3 values of k. So for the case when k is equal to 1, what we have is epsilon ij1 times sigma ij is equal to 0. Now there is a sum over I and j, but we can easily see that if I or j they are equal to 1, this whole thing vanishes. So if you expand the sum and just keep the non-zero terms, this basically would mean is that epsilon 231 times sigma 23 plus epsilon 321 times sigma 32 is equal to 0. These are the only two terms left, and epsilon 231 is a 1, so this becomes sigma 23, and epsilon 321 is a minus 1, so this becomes minus sigma 32 equal to 0, which basically means that sigma 23 is equal to sigma 32. So this is the condition we get on sigma for k equal to 1. Now this equation of course is valid for all 3 values of k. So let's see what we get if we take k equals 2. So in case we have k equal to 2, we'll have epsilon ij2 times sigma ij equal to 0, which basically means that epsilon 132 times sigma 13 plus epsilon 312 times sigma 31 equal to 0, which would give us sigma 13 equals sigma 31. And you must be able to see now that for k equal to 3, we get sigma 1 2 equals sigma 2 1. So what the moment equilibrium has resulted in is that the sigma tensor is symmetric. So these 3 conditions can be summarized in a general statement that sigma ij is equal to sigma ji, that is sigma is symmetric. So I can write in summary that the Cauchy stress tensor sigma is symmetric for non-polar materials. So what that means is that these materials, which are non-polar materials, do not have any concentrated moments. That is, no body couple or surface couples. But if in a very rare case we were dealing with polar materials where we would have some concentrated moments around certain points, then the moment equilibrium is not satisfied. Then the form of the moment equilibrium equation we wrote will be different and sigma may not be symmetric. So you must remember this, that the symmetricity of sigma comes from the fact that moment equilibrium is applicable in the body and the material we are dealing with is a non-polar material. Later, when we talk about situations where the body is accelerating, we will generalize the result further. So now let us summarize what we have seen in the lecture. So we wrote the local equilibrium equations as sigma ji comma j plus rho bi equal to 0, which came from the force equilibrium. But from the moment equilibrium, we showed that sigma is symmetric. So I can also write this as sigma ij comma j plus rho bi equal to 0, because sigma ji is the same as sigma ij using the moment equilibrium. In the symbolic notation, I can write this as the divergence of sigma plus rho b vector is equal to 0. But we'll tend to prefer the initial notation expression. And with the symmetricity of sigma, I can also write the Cauchy stress formula, which was earlier written as T I n hat as sigma j I n j. Now I can also write this as T I n hat is sigma I j n j, because sigma ji is the same as sigma ij for non-polar materials. And in the symbolic notation, this becomes T n hat is sigma dot n. So in today's lecture, we have shown a very important equation, that is the local equilibrium equation. In addition to that, we have also shown that the sigma or the Cauchy stress tensor is a symmetric tensor for non-polar materials, and we will assume that the materials we deal with are non-polar. So we'll simply state the fact that the Cauchy stress tensor sigma is a symmetric tensor. So these local equilibrium equations are very important, and in the tutorial that will follow, we will be using these equations for solving actual problems. So this brings us to the end of this lecture. Thank you very much, and I'll see you in the tutorial next.